Thank you, Dean Baskey. I'd like to add my thank you to everybody here today for joining us for the project showcase. As Dean Baskey mentioned, each student team today presenting was handpicked by their departments for their excellent projects. And we are so excited to have them present to us today. This afternoon's presentations are being videotaped and will be available to view online later. We would like to acknowledge and thank Media Vision and their staff for making this possible. For those of you attending the showcase in person today, we ask that you please silence your cell phones, and we encourage that you stay to the conclusion of the presentations so that you can interact with our faculty and students. Now let's begin the presentations. I will start each one by providing a brief overview of the project and then welcome the team to share their presentation. After each presentation, we will take a short break until the next time certain start. Our first presentation today is from the Electromechanical Engineering Technology Department and is titled Trilateration Autonomous Collector. The team built a self-driving autonomous vehicle that picks up and delivers balls to a designated location. The vehicle uses technologies like sensors, microcontrollers, actuators, and a DC motor control to allow the vehicle to have smooth and precise motion to move in any direction to pick up and deliver balls to the user. I now invite the Electromechanical Engineering Technology team to the podium to share their presentation. Please.
Hello, everybody. We are presenting our project, the Trilateration Autonomous Collector is our vehicle right here. We are representing the Electrical Mechanical Engineering Technology Department. My name is Rebecca. I am MSET major, and with me I have Suhaib, also MSET, and Daniel, ESET major. And our advisor for this project was Professor Dr. Boscovich. Oh, sorry. There we go. All right, so to give an introduction to our project. So for all our golfers and our baseball and softball players out there, you know the worst part of training is having to collect the balls at the end of training, having to go pick up everything. So we aim to make that more efficient by having an autonomous vehicle that can collect it for you. So our goal for this vehicle was to be able to design an autonomous vehicle to collect golf balls. We went with golf balls because it is going to be the smallest design, as if we were to collect softballs or baseballs, it'd have to be much larger. So looking at our vehicle requirements, we come up with a couple of requirements that would be the basis of where we would choose all of our parts. So some of these requirements were being able to identify the amount of balls being collected, know its relative location at any given time, and be able to return to a designated location. From these requirements, we're able to derive what sensors we were going to use, the type of motors we were using, and what microcontrollers we're going to use. And throughout our slides, we're going to show you how we met all of these requirements. So starting off with the mechanical design, on our design, we have two steel plates that sit on top of each other that are connected with standoffs. So on these plates, we have our bottom plate that has our motors and our motor drivers. And then our top plate, we have, on the bottom side of it, we have a Nucleo microcontroller and our battery. And on top, we have another battery, a Raspberry Pi, and all of our sensors. So an essential part of our design was the arm. So for our collection method for the balls, we considered a lot of different methods. So this included a shovel that would be able to pick up the balls and place it in a basket, a conveyor belt that would be able to scoop up the balls and also put it in a basket. But overall, we decided our wire basket was the best design because it was the simplest and most consistent in being able to collect the balls. We also added servos onto this arm because we were worried about the drag that it would cause by turning. And so for our arm, we were concerned about the amount of weight that it was going to be on it because it was going to cause a large deflection. So as you can see in our first design, we have a large deflection. It was moving about 4 centimeters down, and from this, it was going to cause a lot of drag in the vehicle. So by doing a finite element analysis, which is basically doing a computer simulation and looking at how far it's going to move when you apply force to it, we're able to go from a 4 centimeter deflection to 5 millimeters, which was very small, and so we could be able to not cause any drag from the basket being weighing down the whole vehicle. And now we're going to move on to our electrical design.
So for our electrical design, we mainly needed to focus on finding components that were going to help us fulfill all the requirements that we wanted to for this project stated in the beginning of the presentation. We ended up using a Raspberry Pi as our main microprocessor with a Nucleo, specifically the STM32F767ZI microcontroller. It's basically just an ARM processor. We also used Corvo DWM1001 DEV. They're just our GPS. We used a compass. We had a Pixie 2 camera. And we also used Python with the Raspberry Pi to control those, as well as C, C++ to control the motors and tell us how fast we're going to go. How do we determine how fast we're going to go? As you can see in this block diagram, we're going to have the camera and the localization sensors connected to the Raspberry Pi with a serial connection. Those are going to tell us if we've collected the certain amount of golf balls required to go back home. Localization center is just going to tell us where we are within our field of play. Our compass is going to tell us which way we're facing. That way we know how to turn when we want to go back home. Our Raspberry Pi is going to take all that data, parse through it, and through a serial connection to our STM32 board, it is going to tell the motors how fast they should be moving, whether they should control the direction they're going when we want to make a turn, whether they're going straight, and if they need to correct that path, and so on and so forth. We also have the STM32 ARM Cortex telling the servos, controlling our arms right here, whether they should go up or down when we want to make a turn in order to decrease the amount of drag that we wanted to produce. Our image processing was controlled with our Pixie 2 camera. We chose the Pixie 2 camera for its simplicity in using RGB color detection to find our golf balls. We decided to go with orange because it was the easiest color to see in a green field of grass. It also comes with an onboard LED that we used in order to minimize the amount of error in our object detection. And now I will pass this to Suhaib so he can explain the GPS monitor.
So what is localization? That is pretty much knowing where the robot is in the space that we wanted to operate in. For our case, we chose to go with the Corvo DWM 1001 Dev, and we had to buy 5 of these. So we set up 4 stationary anchors. Like I have a representation here. So AN0, AN1, AN2, AN3. AN0 will be our home base, which will be like 0, 0. And within the space, this is where the robot is going to operate. And it is a RF-based technology. Sorry, I was gonna pick it up. But, so this module right here is the RF-based technology. It uses UWB, which is ultra-wideband. It sends and receives data really quickly, and also uses Bluetooth Low Energy. For Bluetooth Low Energy, it helped us set up, for the Android device, and this is how it looks like in the Android device. And so as I said before, 4 stationary anchors. And then this one, the tag, will be set up on the robot, which will be moving and reading the data, giving it over to the Raspberry Pi. And, oh yeah, it updates its position at 10 hertz, which is 10 times per second. So the science behind it is trilateration, which is mainly widely used in GPS systems. So we can see it as like the anchors, as I said before, will be stationary. We have like, you can imagine these 3 as anchors or like satellites or whatever. And as the object is moving, the circles change, and that's how it knows its position while it's moving. And for the radio, the RF, the radio-based technology, it works by the 2-way ranging system. And how that works is it sends 3 signals, and depending on how fast it receives and sends it, that's how it knows like how far it is from each device. For the path planning, as I said before, this bottom left will be the home base. That's if we call the robot, once it's done with its task, it'll always go back to the home base, and that's also where it's going to start. It'll go in this direction. Once it hits this anchor right here, it'll know to make a U-turn. It'll do like a 3-point turn. And we're using the compass for that. So to make the turns, once it hits like 90 degrees, it tells the motors like, hey, stop running. We already made the turn. And it'll keep going, continuing the path, as on until it either finishes it first or it collects 10 balls. After that, it'll calculate the heading that it needs to turn about and head back to the home base. So yeah, as you can see in this video over here, we can say the path planning finished, and it turned about the degree and head home.
To wrap up a project, so looking at how we could have improved it, so one thing we noticed in our testing was that we could have obtained a little bit more reliable sensors. So our most complicated sensor was our compass, which we used for all of our turns. We noticed that depending in the environment we used it in, that we had unreliable data depending on whether it was inside or outside. So inside a building, there's a lot of electrical noise, a lot of lights, different things that are affecting it, but outside there was less of that, so we found it very reliable outdoors. Another thing we could have improved was our arm. So on our arm, we thought that there's gonna be a lot of drag from it turning with the basket being down since it's gonna be on grass. But we found in testing that this actually did not affect it very much, whether it was down or up. So if we were to redesign it, we would make the arm rigid so that it wouldn't be having the lifting motion. So that would take away one thing that we had to have connected. How this could be used in the future would be ideally in driving ranges. So currently in driving ranges, they have manned vehicles that go out and go collect balls. Sometimes this can cause a pause in people being able to go out and golf. So if they had autonomous vehicles out there collecting the balls, then they would be able to continuously have it collect and there would be no pause in being able to golf. Also, it would be able to be upscaled to be used with softballs and baseballs. So in training, you do a lot of hitting practice where you have a bunch of balls out in the field. So if we had this going out there to collect it, you can move on to other tasks and it would make training more efficient by not having to stop practice, collect the balls, and then start again. You'd be able to do some hitting practice, stop, go do another activity while it's going to collect balls, and then continue. And that's all I have. Thank you for listening.